This conference will now be recorded.
Okay, so Florin Unga, as I said, brings here his experience on the characterization of atmospheric aerosol, physical properties, optical properties, and also some experience with the mobile system and remote sensing that he did previously. Eventually, also with some hints on how he can apply his experience in our research related to the attestation of Isac. So thank you to everybody for being here, and Florin, you have the floor.
Buongiorno a tutti. Thank you, Daniele, for this introduction. So I'm Florin, as he recently started a fellowship position here at Isac Lecce, and I'd like to introduce you some insights about aerosol particles from microscopic observation to remote sensing, to online detection of non-anthropogenic air pollution, and mapping the spatial variability of aerosol properties by means of mobile systems. Cannot skip. Sorry, I cannot go next. Okay, sorry. So this presentation is divided in three parts. First part is about the microscopic observations of core shell particle structure and implication for atmospheric aerosol remote sensing, where I will detail about some investigation of the mixing state with particularity on core shell particles model, on measured and retrieved optical characteristics, which is an approach integrating individual particle analysis, remote sensing, and numerical simulation. The second part will be about the online detection of non-anthropogenic air pollution, which is a novel online and real-time measurement setup and application to distinguish the optical properties of black carbon and mineral dust, but as well distinguishing the optical properties of mineral dust from different sources. The third part will be some insights about the mapping, the spatial variability of aerosol properties by means of mobile systems. I'll present some results of several field measurement campaigns involving mobile systems such as vehicles, UAVs, and research vessels which board scientific instruments. So the first part, the microscopic observations of core shell particle structure and implication for atmospheric aerosol remote sensing. It was a work during my PhD. It was a work between two laboratories, Laboratoire d'Optique Atmosphérique and Laboratoire de Spectrochimie Infrarouge Raman, both belonging to University of Lille. Before I will go into the presentation, I just want to remind some properties of atmospheric aerosols. So aerosols have natural sources, and I'm exemplifying here some marine sources, volcanic, desert dust, biogenic, and some typical particles that are emitted from these sources. We also have anthropogenic sources, and here I'm presenting some typical particles that can result from these urban and industrial sources. But these particles, they have a morphology. They have a morphological mixing state, which is the distribution of chemical compounds within and on the surface of each particle. For example, in the left, we have an homogeneous particle and spherical one, while in the right, we have an inhomogeneous particle. It's an internal core plus an external layer. However, atmospheric aerosols is an ensemble of particles suspended in the air, not only one particle. So we can also define the population mixing state of particles, which is the distribution of chemical compounds across a particle population. So we have homogeneous mixture, which is the chemical compounds homogeneously mixed in the volume of each particle, or this is more the chemist's definition, or the physics definition in optics. We have an ensemble of particles which has uniform composition. We also have external mixture, which is an ensemble of different particles with single component in each particle. But we also have an internal mixture, which I will focus now, which is a particle population where different species are presented within one particle. So they are not homogeneously distributed in the volume of each particle. They can be inclusions or superposed particles, and as well coarser particle, which will be the topic. But what is the importance of these properties? So composition and shape are important for scattering and absorbing properties. So aerosols scatter and absorb radiation, which cause the climate cooling and warming. In these figures, I have the intensity of directional scattering in the left for some spherical particles, and in the right for some spheroids particles. Now we can see that in the backward scattering, so from 150 degree to 180 degree, it is a difference between the backward scattering between the spheres and spheroid model. But as we saw, the particles can have complex internal structures. What about them? So as the motivation for this research is that the remote sensing atmospheric applications, they mostly use homogeneous spheres and spheroids model, while in reality the atmospheric particles morphology, it's an internal mix, and we can see in this right electron micrographs with particles collected in urban environment and in desert environment. So the objective of this research, it was to apply field observations and laboratory analysis in order to study the physicochemical properties and mixing state of aerosols collected during specific episodes of elevated aerosol load. Based on this observation and some numerical simulation, we analyzed the effect of microphysical properties on optical characteristics measured and retrieved by remote sensing. And also to investigate the possible parameterization of aerosol structure and composition in remote sensing retrieval algorithms. So the question that I'm raising here is, how often does coating occur on atmospheric particles? On what type of particles? And if it's possible to parameterize? So as one methodology that was applied in this study was to size segregate aerosol sampling according to their aerodynamic diameter, perform offline laboratory analysis at the particle scale using scanning and transmission electron microscopy coupled to EDX in order to get the morphology, so size, shape, and you can get also the elemental composition and the mixing state. As a field observation strategy, so we have applied this methodology in various locations. For example, we have collected particles in Mbour, Senegal, in Western Africa, in northern France in Lille, and in the desert of Negev in Israel. So we have sample particles in urban and desert environment, in various atmospheric conditions, various relative humidity, temperature, in urban pollution, desert dust transport, biomass burning intrusion, sea breeze conditions, both near the surface, so sample near the ground, but also using scientific flights. We have sample collected at the altitude. So to start, I will start a bit with the desert, to discuss about the particles collected in the desert environment in the Negev Desert, Israel, but also in Mbour, Senegal, in the sea breeze conditions. In the left, we have a map of the Negev Desert, and on the right of the collection sample in Mbour, the collection location in Mbour, Senegal. The difference between them is that in the Negev Desert, the collection was achieved at 80 kilometers inland, while in Mbour we were quite exactly at the seashore. So if we look at the inorganic aerosol compositions of this particle sampled, this is a SEM EDX, so scanning electron microscopy. So in the left we have the particles from Mbour, Senegal, so near seashore. In the right, Negev, Israel, so 80 kilometers inland. We have on the top we have the fine fraction, which is PM1, PM2.5, inorganic particles, and below we have the coarse fraction, which is PM2.5, PM10. The conditions are sampling before the sea breeze and sampling of particles during the sea breeze. These particles were categorized into marine, dust, carbonaceous, metallic, dust marine mixture, and other particles. Now, what is really important to see in these pie charts is that both in the fine fraction and we see for both locations, we see that the dust concentration is much more important before the sea breeze, which is normal because the wind is coming from land, and the marine particles are increasing. So the proportion of marine particles is increasing during the sea breeze for both locations. But what is quite important here is that the proportion of dust marine internal mixture is increasing during the sea breeze in both sides, but it's more pronounced in the Negev desert. It's more pronounced at 80 kilometers inland, this increasing of mixture marine dust marine particles. We also have conducted airborne profiling and sampling. So we have installed the HUTAS impactor in an ULM aircraft. We have conducted samplings at 3 altitudes, and I have put on this LiDAR quick look the sampling location and time. So also at altitude, we have encountered various types of particles. So these are particles from transmission electron microscopy. We have an aluminum silicate without a coating, but we have also an aged calcium rich with coatings. We can have also some fresh sea salt, but also aged sea salt. Also internally mixed mineral dust with sea salt. So we have on the left an image with a sea salt mixed with a dust, and on the right a complex structure of particles, which is a calcium-rich particle mixed with sea salt, which also presents coatings. We also conducted the samplings, as aforementioned, in the urban environment. So in urban pollution environment in Lille. The sampling was conducted during a regional pollution event, quite extended. It was in 2014, and this pollution episode is associated with unfortunate death and hospitalization. So this was sampling on a rooftop, but we have also performed sampling in a desert environment, again in Mbour, Senegal, but this time during a biomass burning intrusion, and we have sampled particles at 3.7 kilometers altitude. We see in the back trajectories here that the green trajectory, which arrives at 3.7 kilometers altitude, is coming from the fire region from Africa, which this MODIS figure shows. Now, if you look at the particles, so here I have transmission electron microscopy particles. We have encountered complex morphologies of particles, but also quite simple ones. For example, we have here a tar ball, we have sulfate-rich particles, calcium-rich, but also with coatings. So in regional pollution environment, we have also encountered coatings. But also during the biomass burning intrusion, surprisingly, we did not find much coatings of on biomass burning. Most probably because it was quite fresh, the biomass burning intrusion, but on the mineral dust, which is also presented, we did find also coatings. And here are some examples of particles. Now, how can we quantify these coatings of particles? So the methodology of the image analysis is to measure the projected surface of the particles by counting the pixels inside the image. And then applying an equivalent circle surface equation, and like this we can have the dimensions of particles, assuming that they are a circle. So below we have the methodology for image analysis. It was an automatic one. I'm highlighting first the core of the particles, then the shells, and then the software will extract me and convert me into a surface. So what have we found? We have found that in urban environment that 60% of about 2,600 analyzed particles are coated. In desert environment, during the biomass burning intrusion, we have found only 20% of 5,800 analyzed particles. But we also found a dependency of the thickness of coating on the size of core. So only the thickness of coating on the size of core. And here we disregard the chemical composition. So we look at the total, at the particles overall, not accounting for their chemical composition. And we can see that in both the pollution environment, urban environment, and during in the dust environment, there is a dependency of the thickness of the coatings, which I denoted with hollow, because under the vacuum of the transmission electron microscopy, what is volatile and water aqueous compound is disappearing. So denoted with hollow. So having this dependency between the core and the thickness of hollow, we ask what are the implications for remote sensing. So the question that I am asking is, if we have sensitivity to retrieve any parameter for core shell particle structure, because the problem is that the conventional retrieval algorithms in Aeronet or either for satellites detection, they are based on the assumption of homogeneous and on external mixing atmospheric particles. So can this model, the model of homogeneous particles, can accurately reproduce the optical characteristics of complex mixing states, for example, the core shell model? So for this, I applied a forward modeling. So I have calculated the optical properties for coated particles, but for realistic size distribution of particles. So for a polydispersed particle ensemble, I have calculated the extinction phase function and degree of linear polarization. Then using the grasp model to invert this, we are trying to receive, inverting these optical properties, we are trying to retrieve the complex refractive index or the sphericity of these particles. So these are forward calculations. These are just calculations of optical properties, assuming concentric core shell particle model. I have performed this modeling both for fine mode dominating size distribution, both for coarse mode dominating size distribution. The red line here, it's for not coated particles, so an homogeneous particle. The complex refractive index for core was for a dust one, so 1.5, spectrally independent, and a bit of absorption. While for shell, so for coatings, I have put on complex refractive index typical for ammonium sulfate with no absorption. And I'm just here I'm presenting some differences between the homogeneous model of phase functions, so of intensity of intensity of angular scattering, and also on the degree of linear polarization. So it's important to say here that the size distribution remains the same. So we just shrink the core, but the total particle remains the same. This is in order to remove a possible effect of the size distribution over calculating the optical properties. So keeping the size distribution, but varying the internal structure of particles with two refractive index, we see that both the phase function and the degree of linear polarization are changing. I have also calculated the single scattering albedo and LiDAR ratio as a function of shell contribution to the total ratio. So we have used the same conditions. And what we can see here is that the single scattering albedo, so we have two wavelengths here for 40 nanometers and 1.02 micrometers, sorry. And we can see that by increasing the ratio of thickness of shell to the total particle, single scattering albedo is changing. It's also changing for the case of coarse mode dominating, but also the LiDAR ratio is changing. So in this case, now we are trying to retrieve this complex refractive index using the optical properties calculating before. So we have performed sensitivity tests of retrieval in this partial model for the same fine mode dominating case, which I'm presenting here, for three types of measurements. So I define like the photometer-like measurements, which they have a spectral extinction, they have a spectral phase function, and the scattering angle between 0 and 120 degrees. Satellite-like, which is the spectral phase function, spectral degree of linear polarization, and scattering angles between 65 and 165. But also an ideal case, assuming that we have an instrument that can measure the spectral extinction, spectral phase function, spectral degree of linear polarization, and on full scattering angles from 0 to 180 degrees. So what we can see here that, so with black we have our input into the model, and with colored we have the retrieved one, so the inversion. And we can see that in this case of fine mode dominating size distribution, we can retrieve quite well the optical properties. So the real part of refractive index and the imaginary part of refractive index are in between of what we input for core and shell. But when we go to the coarse mode case, so we keep the same conditions and refractive index, we can see that we are retrieving quite strange behavior of complex refractive index, especially when the thickness of shell to the total particle is 0.4. And this is the case for all the types of measurements. So in conclusions, we have the particle coatings were evidenced by transmission electron images as transparent material, a halo surrounding a core particle. And in case of fine mode, the homogeneous model reasonably reproduced the core shell optical characteristics, which is in line with other studies. But in the case of coarse mode and other measurement type, the effect on retrievals is manifested stronger. It was not tested previously before. But in fact, this was the answer that we were looking, because by not retrieving the same properties of a core shell particle with an homogeneous model or spheroids or a mixture of these homogeneous and spheres and spheroids, we cannot retrieve the optical properties. That means that we have sensitivity to retrieve such parameterization for remote sensing. So this core shell structure can have unique optical characteristics, which means potential sensitivity of some type of measurements to the core shell structure. Now I will switch to the second part of the presentation, which is about online detection of non-anthropogenic air pollution. It was a project between the Cyprus Institute, the Joseph Stefan Institute from Ljubljana, Slovenia, and the Aerosol Company from Slovenia. So as a main goal of this project, it was to develop an online and real-time measurement setup and application to distinguish the optical properties of black carbon and mineral dust, but as well to distinguish the optical properties of mineral dust from different sources. We know that black carbon is strongly absorbing light across the entire visual, near infrared and near ultraviolet spectral range, while mineral dust is relatively transparent at solar wavelength, which results in light scattering, but is absorbing at short wave. You can see in this figure, for example. So, but why do we need a new model? It's because the detection of mineral dust is usually performed offline in or post data collection, for example, analytical microscopy, as I previously showed. We have remote sensing techniques, either from satellite bases or from ground base. We also have online applications, for example, PSIC. However, these techniques, they require a large commitment of analytical resources and time. So in order to overcome this, we are proposing a setup by constructing from 2 etalometers, AE33, so 7 wavelength etalometers, one coupled with a PM1 inlet, here in the right, and one coupled to a virtual impactor and a 100 per liter per minute pump in order to concentrate force particles in the measurement. Then the light absorption on mineral dust is determined by the equation, this equation. So we just subtract the absorption of PM1 from the VI absorption measured, but we have to divide by the enhancement factor, which is determined experimentally. So this enhancement factor is how much we enhance the size distribution by using the system of virtual impactor and 100 per liter per minute pump. Then to calculate the mineral dust concentration, we divide the absorption of mineral dust at short wavelength to the mass absorption cross section of dust. So in order to verify this method, if indeed we are enhancing the concentration of coarse particles, we have also installed the third etalometer, which is measuring total suspended particles, which is here with red. So here I'm presenting just the statistics, the average, 1 year average, 2018 and 19, for the absorption at 470 nanometers using these 3 setups. So we clearly see with the green that using the VI setup, we are indeed enhancing the absorption. So this setup was installed into location in Cyprus. So why Cyprus? Because Cyprus is an island located in the Mediterranean Sea at the intersection of pollution from Europe, dust from the Middle East, dust from Sahara, but as well Cyprus is impacted by the marine aerosols and local anthropogenic emissions. And here in these images, I'm showing the air quality stations where the instruments are. And the difference between the 2 stations are about 30 kilometers. So this station is an urban regional background station, or this one is an urban station, the Nicosia. So to verify the validity and robustness of the absorption via PM1 method, we just straightforward compared for regional background site and for the urban site, we just compared the PM dust calculated with blue, which is calculated from our absorption data, and we compare it with PM coarse. So PM coarse is PM10 minus PM2.5 from TOM EFDMS data. And on the bottom, for the urban site, we compare the PM dust from absorption data from our method to the PM dust obtained from PSIC calcium data. We can see that we have a good trend between these measurements. And if we look at the correlation plot for regional background site and urban site, we can see that we have quite a good correlation for the regional background site, because here we expect to have don't have the pollution from the urban cities. But for the urban side, we don't have quite good correlation. And this is very well explained by the fact that black carbon can be larger than 1 micrometer. So we have conducted this air masses back trajectories analysis. We have for 1 year, we have flex part statistics of 72 hours backward trajectories run each 6 hours. And if we look on this on the spectral absorption and we try to correlate it with the source region, we clearly see that both for regional background and both for urban site, we have a spectral dependency of the absorption coefficient when the air masses are coming from the Middle East and with yellow, and from Africa with red. Now, this effect is much more pronounced in the case of regional background site, and as aforementioned, it might be different mixing of particles in the one site having much more pollution. So if we look on the absorption angstrom exponent between 370 and 660 nanometers, we clearly see a higher absorption angstrom exponent for particles coming from the Sahara Desert and the Middle East. And the PM1 absorption angstrom exponent remains quite the same for different incoming air mass regions. So in conclusion, we have developed and tested an online and real-time mineral dust detection setup. The method have been validated by intercomparison either with filter-based chemical composition, either with TMFDMS or online PILS-IC. They show a strong potential of the absorption of the IPM1 approach to perform quantitative determination of PM dust in PM10. Spectral absorption coefficient varies as a function of the incoming air masses, and we have a higher absorption angstrom exponent for coarse particles during transport from Middle East and Sahara. And going to the part 3 of this presentation, so it's about the mapping the spatial variability of aerosol properties by means of mobile systems. As context and motivation for these studies are that the majority of ground-based aerosols observations are limited to fixed locations, which is narrowing the knowledge of their spatial variability. And as methodology, in order to overcome this, several systems have been developed to explore the aerosol vertical and spatial variability. And these systems also horizontally. So these systems can perform on road mobile measurement by means of vehicles, UAVs, and research vessels boarding scientific instruments. So in this Climate Bio project, I have been involved in measurements with a mobile system. Here it's an image with a car. So it has a LiDAR included, it has an aerosol spectrometer, we have a mini brass aerosol spectrometer, meteorological probe, we have an isokinetic sampling probe for the aerosol spectrometer. And this car was also equipped with a plasma mobile sun photometer. So I'll just present a few applications of this system. So first we have validated our PM calculations of the mini VRAS, so PM10 and PM2.5 here on the left, with measurements from air quality stations. And we have obtained a very good correlation. So we have investigated the PM spatial variability in a transect from northern France, from Lille to south of France, the entire coast of Azure, and back to north of France. So we have explored this spatial variability of PM10, PM2.5, PM1, and we have encountered different contributions of PM and different variability. But an additional application can be the comparison of air quality forecast models with measurements. So here on the right, we have an forecast model of PM10, and we have with these stars are the measurements of air quality of PM10, and we have these measurements from Lille to Paris, and we have obtained same variability of PM10. And if you don't see here the color, that means that our measurements are in the same range as the air quality forecast. So we can also use this as an application. Additionally, we can perform on-foot mobile measurements. So these were done by a student, an Erasmus student that I was coordinating, and she also written a small paper. She was a bachelor student. So we have installed an OPC N2 with a GPS and in a backpack, and the student has performed the measurements on foot, but the application was to see the pollution inside the metro ride during circulation and compared to the outdoor pollution. And here we have the PM10 and PM2.5. Sorry, PM10 and PM10. We have from Minipras, so we have here an instrument more precise for accounting the size distribution and calculating the PM10, and we have also an OPC. Both measurements shows same variability, and what is important here is to see that whenever we were we were doing measurements inside the metro during the transit, we have more pollution, and it's mostly dominated by fan pollution. You can see with the green, it's PM1. And what is interesting is that this higher pollution is when the metro was quite deep underground in the line. Another application of use of cost-effective sensor for UAV measurements. So this can be used for boundary layer height characterization, flux measurements, plume characterizations, validations of derived aerosol properties from remote sensing, quantification of PMX inside and above the boundary layer as well. So we have installed an OPC AlphaSense N2 in a quad. We have performed the measurements up to 1.5 kilometer altitude for each and a half hour, and we could see the variability, how the boundary layer height is increasing, and also the morning traffic peak we have, and the distribution of the morning traffic peak on altitude. I was also involved in mobile shipborne sun, sky, lunar photometer, and sailometer observation during the Aqaba campaign. So we have boarding scientific instruments on a research vessel, and this was to see the spatial and temporal variability of aerosol properties from remote sensing. So we have performed measurements from France towards Kuwait, and we have encountered different aerosol variability, and we have installed a sailometer to see this. We have encountered ship pollutions in the Suez Channel, in the Red Sea near the Mecca port. We have very dust storms seen here in this sailometer quick look. And in Gulf of Oman, we have encountered petrochemical activities. Now, these are determined also by an increased aerosol optical depth at 440. And for example, in the case of the dust storm, here we can see that the angstrom exponent is quite low, it's below 0.4. While for the petrochemical activities of fine mode aerosol pollution, the angstrom exponent is increasing even after 1. We have also performed mobile ship. We have also performed scientific flights from the ship. This was with the purpose to try to validate as well, to intercompare with the mass concentration derived from the sun photometer and sailormeter measurements using just a flat curve. Sorry. The idea is that the sailormeters and lidars, they cannot very well estimate the measurements at the ground level near the first few hundreds of meters, or can be even higher than 1 kilometer. So we try to compensate this by performing flights with light sensors, low cost effective sensors in this region. And we can see here in the left, so we have the sailormeter mass concentration, and we also have the determined mass concentration from optical particle counter. We see that both measurements are in the uncertainty range of them. So in conclusion, these cases exemplifies the use of mobile systems which proved to bring new insights for atmospheric aerosols observation. And with this, I am thanking you for attention, and if you have any questions, please here to answer. Thank you.
Thank you, Florin, for this presentation, which give a global overview of several aspects of your research. And now I think that we can start eventually with the questions that can be made online if you want directly to speak, or eventually on chat. Yeah. So I don't know if there is any question or curiosity that you want to ask to Florin. Okay, so I will start to break the ice here with I have a couple of curiosity on regarding this the comparison that you showed for Mbour and Negev, like that kind of source apportionments, let's say, with the dust marine. So that was on number of particles or on mass, was not clear.
Yes. These are performed on number of particles. So we have about 500 particles per each size fraction. Yes. It's it's for particle number.
Okay, yeah, because especially for the force fraction, it can a little change if you make on mass the same analysis.
Yes.
And another question, which is more theoretical than practical. I mean, because I'm not sure if you have any answer of this, but the aspects regarding the coating of particles, like you know, external mix or internally mixed and so on, it clearly has some effect on optical properties. Do you know if this can also be some effect on health or on oxidative potential of these particles, or not? If I mean, the coating could have because very often I saw correlation of some geological outcomes or health indicator with just the composition, but do you think that the coatiness could have eventually effects on this?
Yes, indeed. So yes, I have some answer to this question, and yeah. So what happens is that water can be adsorbed on the surface of particles, and for example, they can get stuck in these irregularities of this part of the particles. And furthermore, more compounds will be stuck in the liquid coating. It can be metal compounds, it can be different kind of pollutions. So this will also change the chemical composition. It can make it more oxidative, if I'm not mistaken.
Yeah, that could be interesting, because I don't know exactly if there are studies on these aspects already done. I don't know if Francesca knows something about that this aspect, but anyway. Is there other questions or curiosity or comments on the work of Florin? And that could also there be some hints for future collaboration with the experience of Florin. No, so probably. I can also ask
colleagues if they have other questions.
Yeah, I don't know if someone there in presence has a question. Eventually, you can ask. Or you have been very clear, or you gave a lot of information and people has to process them. Okay. So I think that we can close here, and I wish to thank you again, everyone, for participation to this seminar, and Florin for the nice speak. And Florin will stay here and will work with us still for a long time. So eventually you can have also contact outside of this seminar. So I will stop the recording, and thank you to everybody, and goodbye.
Thank you. Thank you. Thank you.